Hi. Oh, sorry. Hi, everyone. I'm Ryo Takashi from Tokyo University. So today, I'd like to share a project named picoRing, a battery-free ring for subtle finger input. And this work is collaborated with Eric, Roger, Shu, Wall, and Benko. So the computer mouse is one of the essential input devices supporting subtle finger inputs such as click. So what is the form factor of the mouse in wearable computing? Smartwatch or wristband devices are famous, but still needs a bit large finger motion to detect the finger gesture away from the wrist. On the other hand, ring devices are great for capturing even subtle finger movements, since the ring near the finger can stably detect the micro finger movement. But the ring still needs to be bulky and has a short lifespan. So this is because the ring needs a bulky battery into the tiny ring for wireless communication, mainly so BLE. So while some researchers are good at hiding the battery, so typically the 2 times larger battery should be installed in the normal ring, even when the ring continuously uses BLE only for a few hours. So the bulkiness and the short lifespan are the issue. So to solve this challenge, we present picoRing.
picoRing enables battery-free and wireless input rings that support pressing, sliding, and scrolling interactions. A wristband can detect the passive response from a ring. Using various passive switch, we can design picoRing press, slide, joystick, and scroll.
So this is, okay, say again. So picoRing allows the battery-free ring coil to wirelessly communicate with the wristband coil and detect, press, slide, and scroll, so basic subtle finger input interactions. The point is that we replace the BLE with a passive resonant coil and replace the sensing module with a passive simple switch. So to our lightweight, sustainable, and wireless rings, the ring meets the 3 requirements: so low powered and communication with nearby wristband and reliable subtle finger input. So prior work has proposed low power wireless communication such as RF backscatter and NSC. While the 2 techniques are available for various applications, they are not suitable for pairing the ring to the wristband, since the backscatter needs the large antenna in the ring, and NSC supports only a short-range communication, so around 1 or 2 centimeters. By contrast, picoRing meets the 3 requirements, so no power for ring operation, and stable ring with a wristband, and high SNR. So picoRing uses a pair of the wristband coil and the ring coil, and the wristband monitors the ring resonance states with low power wireless communication, and the ring passively converts the subtle finger input into the unique resonant change. So let me explain more detail. So the key idea of picoRing is to use PIT, or passive inductive telemetry. So PIT works as follows. So when the user makes the subtle finger input on the ring passively changes its resonance state by passive switch. So this resonance state means the resonant frequency determined by the ring's inductance and capacitance change. So here we change the ring resonant frequency by changing the capacitance through the on-off of the switch. On the other hand, the wristband coil generates a weak magnetic field and coupled with the ring coil. And this magnetic coupling between the coil causes a peak in the wristband output, so near the ring resonance frequency. So that's why the wristband can estimate the ring resonance state by monitoring the peak. So summarily, the PIT allows the ring to operate without power and allows the wristband to monitor the ring state with low power. Oh, sorry. So this is the peak via in the wristband coil. So, but the PIT has a 2 challenge when we apply the PIT to the ring one. So first, how to design the passive ring coil. And the second one is how to detect the ring resonance state by the wristband away from the ring. So basically, the wristband coil estimates the user input by monitoring the ring resonance state, so which is determined by the ring inductance and capacitance. And the inductance is determined by the coil size and turn number. So we try to develop a passive variable capacitors, which changes its capacitance by the user's input. And there are three options, so tactile switch, potentiometer, or photodiode. And among them, we choose tactile switch, since we simply connect the chip capacitor to the tactile switch and can create the passive variable capacitor. So such design is easily designed and low cost, and the main point is that the capacitance change is user independent, so user hand or ring size. So here we implement the picoRing press, slide, and joystick and scroll, so using commercially available mechanical switch, like the slide switch, or joystick switch, or magnet switch. Okay. Also, the second challenge is the PIT is not so sensitive similar to NSC. So basically, the PIT supports short-range communication of about 7 centimeters. But to pair the ring with the wristband, we need to increase the reader distance around 13 centimeters or 15 centimeters. So we need to increase the reader distance by at least two times. And to increase the reader distance, we enhance PIT sensitivity by developing pair of the sensitive ring and wristband coil. So PIT sensitivity or reader distance is mainly determined by the three factors: so distance between coils, reader frequency, and coil turn number. And the distance is fixed, so the distance between the ring and wristband is fixed. And the frequency is mainly chosen among one of the NSC frequency bands, so here 27 MHz. That's why we need to increase the coil turn number to amplify the peak signal. So if we use low turn coil, the peak is too small to detect. But increasing the coil turn number at 27 MHz is a bit challenging. So this is because the wavelength is too short to develop the long turn coil, so which has a long wire. And the short wavelength effect allows the long turn coil to work as capacitance, not as an inductor. That's why we use distributed capacitors, so which insert multiple chip capacitor into the large turn coil at equal intervals. And because the capacitor splits the long wire into the multiple small coils, and each coil is short enough to work as an inductor, and the series connection of such a small multiple coils becomes a single large turn coil. That's why by using the distributed capacitors, we can create the large turn coil at 27 MHz, so at tens of megahertz, and enable to increase the PIT sensitivity. So actually, the entire system of picoRing is a bit complicated. So we use additionally bridge circuit and the peak signal detection. But while we skip the detailed explanation, please check our paper for more detail. And let me show the two evaluations of our enhanced PIT. So first, we check the PIT performance by changing the distance between the ring and wristband. And as you can see, the available distance, so maximum distance is 15 centimeters, so which is enough to pair the ring with the wristband. Also, we check the finger bending like this, since the misalignment between the coil also weakens the magnetic coupling, but the enhanced PIT works against the natural finger bending. And we also evaluate the PIT capability by measuring the SNR, so signal to noise ratio. And at first, we checked we need to, the SNR must be over 10 to detect the peak, ring peak with almost no error. So as you can see, our enhanced PIT can increase the readout distance by approximately 2 times, so which allows the wristband to stably read out the ring resonance state, so pressing, sliding, and joint scrolling. Also, we evaluate the SNR when the picoRing works near daily appliances and metallic items. Although the daily appliances, such as wireless charger, generate a strong EM noise, but our approach is robust. But when the metallic ring is quite near the ring coil changes its resonance state. So this is one limitation. And also, the other 2 limitation is we use a bulky battery for the wristband to monitor the frequency response. Also, each ring coil supports only one input interface because they are equipped with only one switch. But the use of the portable nano VNA, so which is a portable VNA, also multiple functional input switch could solve this challenge. And finally, let me show the application scenario of our ring. So our ring is a good companion for AR glasses and head-mount display. So our ring could become the ubiquitous finger input interface. So let me summarize our work. So toward battery-free and wireless ring input device, we propose picoRing, so which uses enhanced PIT and also fully passive ring design. So that's all, thanks.
Yeah, please. If you have questions?
Yes. Hi, Rio. I'm Nathan from Carnegie Mellon. Great talk. I was curious, you mentioned this example of when you changed the finger angle, the coupling decreased.
Yeah.
Did you also look at that as a potential source of input? Like you could maybe track the pointing angle of the finger based on the coupling level?
Yeah, it was possible. So it's kind of the Aura ring, but passive version. So yeah, one future application is to combine the finger tracking and finger gesture by monitoring the peak height and peak position. But yeah, that's all.
Okay, thank you.
Hi, Cedric Honnet from MIT. I have a question about an equivalent circuit made by Texas Instruments that seems to do exactly the same. They market it as capacitive to inductance converter. Did you ever compare the performance of their system with yours?
Oh, say which one?
Capacitive, sorry, inductance to digital converter
Inductance digital component?
by Texas Instruments.
Oh, I didn't. But
Okay.
it's
Thank you.
Good question here.